CTC 114. Guess what we have in store for you today? It's another lab experiment, and this lab experiment is going to focus around water hardness. Now, what is really water hardness? What is that all about? I mean, can water actually be hard? Like knock, knock, knock hard? No, that's really not what we are referring to here at all. What we are referring to is this dancing little calcium and dancing little magnesium have a grand old time right here, dancing in the rain. That's really what we're focused on. Water hardness is actually the amount of calcium, which of course is abbreviated Ca, and magnesium, which is of course abbreviated Mg, in a water sample. And this water sample could come from anywhere. It could come from your well. It could come from your faucet, so whatever comes from your kitchen spigot or your bathroom faucets at home. It could come from a river, a lake, a stream. It could come from a pond. It really doesn't matter where the water comes from. We can titrate, that's the key word, titrate, yet again, that particular sample for the amount of calcium and magnesium that might be present. So this laboratory video is going to walk you through the importance of water hardness and why we would really want to measure this in a sample in the first place, and then give you a little bit of insight on what you're going to be doing in the lab when you show up. So let's first start talking about water hardness in terms of chemistry and the way that this is going to go and play out. So with water, even the drinking water that comes from your faucet, folks, you've got two sets of compounds that could be found that we can discuss here. Now, think of this as alphabet soup. Alphabet soup, there's tons of different things that could be there. But there's two classifications of major things, and one of those is going to be a cation. So a cation is an ion, and that ion basically means a charged atom. And this charged atom could be one of two things. It could be negative or it could be positive. Well, I see the T, and therefore this is a positive atom. So here's my little atom right there, so cute. And then up here up above, we have a positive charge. Well, the other thing that we could find maybe in drinking water samples or river water samples or any type of water source would be a classification of compounds called an anion, A-N-I-O-N, and I see the N that is in that name. And that N, again, is a ion, which means a charged atom, and this is going to be a negative containing species. So we'll draw another cute little atom right here, and we'll put a little negative up above them, so that way we can look at these and say, oh, there's a positive charge. That's a cation. It makes us sound smart. That's why we use it. And then, oh, look, here's an atom. It's negative. So we're going to call that an anion. Okay, that is the terminology that we're going to have to start using while we are in a laboratory environment. So drinking water samples, folks, is, again, an alphabet soup of different types of compounds and different types of ions that we might see on the inside. So we could have tons of positives here. And then we could also have tons of negatives that are floating around, as well as everything else. It's kind of disgusting when you really sit back and kind of think about it in a chemical term. It's not just H2O. It might look like it's just H2O to you in the glass, but it is not. And it's far from it. So within this particular world, let's talk about how cations and anions get formed first. So in order for something to be a cation, folks, here is the atom, and the atom has a certain amount of protons and a certain amount of electrons and a certain amount of neutrons. And protons carry a positive charge, electrons carry a negative charge, and neutrons, of course, are neutral. All right, so we have protons and we have electrons and we have neutrons. And all of this information can be found from the periodic table. All right, so if I go back and I take a look at something like calcium, all right, so here's calcium, it's Ca, and let me pull up a periodic table so that way you can take a look at it. So here's a periodic table, and we need to find calcium. So if I try to find calcium, it's right here, and there's a number up at the top that's 20, and then this number down here at the very bottom, it's probably too small for you to read, but we're going to round this off, and we're going to say 40. All right, so the top is 20, and the bottom is going to be 40. Here's a zoomed in picture of that calcium that we were discussing. All right, so 40.078, but we are going to round it off to 40 to make the math simple. All right, so the reason that I'm bringing this up is because this kind of is important, folks, when we talk about atomic structure and when we talk about ions getting formed, because this is what happens. If this is calcium, remember that atomic block on the periodic table had a 20 up at the top. Well, that 20 represents the number of protons. That's what that 20 means. That's the atomic number. That's what we call that, atomic number 20. So we have 20 protons. And then if this atom is neutral, folks, neutral means no charge. So that means we also have to have 20 electrons as well. That is what that number represents. All right, so to get the number of neutrons, this is a neutral charge. It does bring some mass to the atom. The proton brings mass to the atom. The electrons, though, they don't. There are little squirmy things that we just don't really care about sometimes as far as the size and the amount of punch that they can give us. So those electrons, little bitty things that we don't really have to worry about, but quite honestly, they are the most important part of the atomic structure, which drives the chemistries forward. So never forget that electrons are one of the most important things that we look at. But the number down here at the bottom of the block, right? The atomic number 20 was up here at the top. And then down here at the bottom, if this was the block of the atom that I'm looking for, that's at a 40. We rounded it off. So neutrons and protons give us mass according to the atom. Compared to the electrons are insignificant. We almost say that they're zero, quite honestly. The mass of an electron is 1 over 1837. That is 1,837ths of a unit. That's super, super tiny. That's like 0.005, math in my head. All right, so what this means is that if I can take this top number, which is the atomic number, and if I can subtract that from the mass number, so 40 minus 20 will give me 20, and this is going to represent the number of neutrons that we have in the atom as well. So these are the basic calculations that you might be learning in a general chemistry class, and this is how we do them. So the atomic number is 20, and then the bottom number is 40. So 20 from 40 gives me 20, and it just so happens to be 20 down the board. It's not going to work out this way every single time, meaning all the numbers are not going to be identical. A lot of them are. So if I go back to the periodic chart, if I take a look at magnesium, okay, well, 12 protons, 12 electrons, and 12 from 24 is about another 12. And we got this weird little number here. But what you have to keep in mind is that the mass number is the average of the isotopes. So we've got fat little atoms, we've got skinny little atoms, we've got normal size atoms, and we take an average, and this is the average, which is why they are not completely even. All right, so 12, 12, 12. Okay, well, if I take a look at beryllium up here, it's got 4 proton. It's got 4 electron, and 4 from 9 is 5. So this is a case where they don't match, and I have 5 neutrons in that atom, along with 4 protons, and then another 4 electrons. If I take a look at lithium, okay, well, lithium's got 3 protons, it's got 3 electrons, and 6.9, this is pretty close to 7. Let's just say 7. So 3 from 7 is going to be 4. So yet again, they do not match. So some of these do match in numbers and some of these don't, and it's okay if they don't. I mean, that's kind of normal. That's what we expect to see. It's no big deal. So we are focused on the magnesium and we are focused on the calcium. Now I'm going to show you another trick from the periodic table. Magnesium and calcium, folks, it is in the second column of the periodic table. Look up here at this Roman numeral. You see that Roman numeral that says 2A. There's 1A and 2A. And look at this. This is B, so we're not going to be concerned with it. And then if I skip over here, that's 3A and 4A. And the next one would be 5A. They're on here for a reason. And the reason that that Roman numeral is there, that Roman numeral is present because that's the number of what we call valence electrons. All right, so what on earth is a valence electron? Okay, well, a valence electron basically means a free electron. It's like a free man or a free woman. I mean, you're single, you're not tied down, you've got no kids, you can move from city to city, you can go wherever you want to go. That's what these valence electrons are. They're bachelors and bachelorettes. And those valence electrons can actually be freed up and they can participate in bonding. They can participate in chemistries. And if those valence electrons do participate in chemistry, well, they're either going to be lost or you're going to gain them, kind of like in form of children. So it really depends on what you want to do with your life. That's what these atoms are. Do they want to go out and be single and lose those kids from the house? Or does the home want to bring in extras? And now you have some kids and some hungry mouths to feed at home. Well, in the case of calcium and magnesium, we have two valence that those atoms carry, which means two of the total 20 are valence electrons that can easily participate in reactions. Well, in both the case of calcium and magnesium, these two electrons, we lose them, folks. We lose them. You have $2 in your bank account and you spend those $2. You've lost those $2. Well, now you have 0 in your bank account. Okay, well, what if you were neutral in your bank account? Your bank account said 0. I hope it never says 0, but let's say, just for sakes, that it did say 0 one day that you woke up. Maybe you bought an extra Starbucks coffee the day before that you shouldn't have bought, and that just made you out to 0 with no pennies. Perfectly neutral bank account. And then you lose $2 because you go out and you spend $2 that you thought that you had and you didn't, and your transaction was approved because your bank allowed it to happen. In the olden days, you would write a check for $2. They would just take it at face value and say, okay, this is $2, it's good. And sometimes it wasn't, and that check would bounce. Bounce, bounce, bounce. So if that happens, you have $0 in your bank, you spend an extra $2 that you didn't have, you become negative, right? You go in the hole. Well, folks, if you go in the hole in the world of chemistry and in the world of a cation, what this means is that we start off with calcium, and this calcium has 20 electrons. That means 20 negative charges that it has. Well, let's say that this calcium loses those 2 valence electrons because that Roman numeral up at the top was a 2. Well, if we had 20 and it loses 2, we've got 18 now. 18 electrons. That means 18 negative charges that we have. But keep in mind, protons. What's going on with the proton number? Nothing. the proton number stays the same. So if a neutral calcium has 20 protons, that's 20 positive charges that it has. And if the calcium loses 2 electrons, well, it didn't do anything to the protons. I didn't say anything about the protons. The protons stay there. In order for it to be calcium, it has to have 20 protons. If not, it's a different atom. So what this means is that there's 20 positive charges that are still present. And now look at these 2 charges. This is no longer neutral anymore. It's not neutral. What I have is 2 more positives than I do negatives. And because of that, we write this as calcium plus 2. And this, ladies and gentlemen, is called a cation. Some people call it cation. Don't call it cation. I mean, you could, but people would look at you like you've got like 3 heads or something. So it's a cation and an anion. That's what they are. All right, so I look at this calcium plus 2, but that's not the only thing that we're focused on in this lab. We're also focused on magnesium plus 2s. It's in the same column. The difference is the number of electrons, but the still same kind of concept happens. You have a certain amount of electrons, you have a certain amount of protons. Magnesium, because it's in that second group number, is going to lose 2 electrons. And now I have 2 more positives than I have negatives, which means that this is a magnesium plus 2. Folks, that is what we are measuring in the water hardness lab. We are going to be measuring the cations, and these cations in particular are going to be magnesium, and they're going to be calcium. Now, we can measure other things as well. Iron, manganese, copper, any type of metal. Any type of metal, we can measure them in a laboratory, but that's not really hardness. Total hardness, water hardness, we are looking at calcium and magnesium specifically. Well, we can measure anions as well. They're present. These anions are things like fluoride, because they don't want your teeth to rot out. Chloride and bromide, because they don't want you to swallow bacteria in your drinking water, so they disinfect it because of that. Nitrates and phosphates that could maybe be runoffs from fertilizers and that type of thing. So all of these chemicals are negatively charged, and they can also be found and discovered in the lab, but we're not going to be focused on those either. We're only going to be focused on the calcium and magnesium, because that is what water hardness is defined as. Now, we've got different classifications, and we can call water hard, we can call water soft, we can call water moderate, we can call it extremely hard. We've got some different classifications that we can use when it concerns water hardness. So here are the general guidelines. These general guidelines are basically stated out in literature. I didn't make these numbers up. They come from somewhere. So a range of 0 to 60, and I'll talk about this milligram per milliliter in a minute, but a range of 0 to 60, you will have what we call soft water. And a lot of people want soft water. This is kind of the go-to. That's what they like. I'll explain that as well in just a second. Well, if you go above a 60, so now 61 to 120, so notice we doubled that amount, 0 to 60, and then 60 times 2 is 120, right? So 61 to 120, you are in the realm of moderately hard. Then it can go higher. 120 plus another 60 goes to 180, so 60 is the increment here. And 120 to 180, you're looking at hard water. And then if you're greater than 180, then you have extremely hard water. Now, is one of these good? Is one of these bad? No, not really. As far as your health is concerned, there is nothing that extremely hard water does to your body. Now, some literature says, oh, it makes kidney stones. People have kidney stones more common on extremely hard water. Well, some studies show that and some don't. They also go back and they talk about blood pressure. It makes blood pressure go up. Well, some studies show it, some studies don't. So, overall, the general consensus is that water hardness, it's really just a measure of the type of water that you have. It's not really a measure of contamination. We do not look at this as contamination. And to take that point even larger, if you go to the Environmental Protection Agency, you do not see a guideline that they give for drinking water on water hardness. We can measure it, we can report it, we can log those numbers, we can study those numbers. But if someone's water tests extremely hard from their faucet, it does not sound an alarm to the EPA, because the EPA, quite honestly, they don't care about it. It's not regulated, unlike some of these other compounds that we might find in a drinking water sample. Now, even though it doesn't cause health concerns, and even though the EPA is not really focused on it too much, we still measure it. But some people do have a concern with it. And the reason that they have a concern with it is because of everything that it can do, folks. And if you have extremely hard or hard water, it is a nuisance. Because what will begin to happen is that scale buildup will begin to happen on the inside of your pipes. It will happen in your showers. It will happen on your shower doors. If they're glass, you'll clearly see the scum and the scale that hard and extremely hard water leaves behind. It can get into your toilets. It can get into your bathtubs. It can get everywhere. And over time, you can actually lose water pressure because of it as well. And the reason, look at here. Look at these pictures. These pictures are the insides of piping that hard water has traveled through over the number of years. And look at the way it looks on the inside. You begin to see this precipitation that begins to happen on the inside of the pipes. And we do not want to see that. And the reason that we don't want to see this is because we begin to lose water pressure. And folks, I know as good as you know, there's nothing better than getting into a shower and cranking on the shower head and having that forceful water come out of that shower head onto your body in the wee hours of the morning or at night, depending on when you take a bath, if you take a bath, all right, or a shower. All right, so this is the problem with water hardness. So this is one of the reasons that we do like to measure it. We do like to report it. People do request it because it is something that's pretty common that we would like to just monitor over a course of time. Hard water, you know that you'll have hard water if it feels slimy or if it leaves any type of residue on your hands. So if you wash your hands in hard water, it will be kind of slippery. And you might think, oh my God, I didn't really wash my hands that well. What is this kind of grease or oil that's still on my hands? Well, some people think that's normal because some people have grown up with hard water all of their life and they don't really know what soft water actually does. Well, in addition to that, in hard water, soap and shampoo is also harder to lather. And once again, I know you know that there's nothing better than getting a really nice body wash or shampoo or conditioner and having it suds up. If it doesn't suds up, you feel like you're not getting clean. That's just natural tendency for us as humans to kind of go through. The same happens with toothpaste. If you put toothpaste in your mouth and it doesn't really suds or foam, you're thinking, well, this toothpaste is kind of crappy. So you throw it away and you go get something else that gives you this nice foam and this nice lather. The same thing happens in a shower or in a bathtub with hard water. It is harder to lather. But again, folks, depending on where you live in the country, hard water is normal, and maybe you never thought that things should lather the way that they do, like they do because of it. All right, so groundwater, of course, that's kind of self-explanatory. Groundwater has harder values on average than your public water supply. So if you pay a water bill and that water bill goes to a place here in Wilmington like CFPUA, or if you're over in the Leland, Brunswick County, you're looking at H2Go maybe for your water company and so forth. If you are paying a water bill to a company, that is what we call a public water supply, and that public water supply typically is on the soft range because they condition the water for the most part. But if you are getting your water from something like a well, then you will have harder values as far as water hardness is concerned. All right, so over here to the side, you're going to see soft to hard, and here you'll see 0, and it says ppm all the way down to this scale, 425. So these numbers can get quite large depending on what they are. Now, I want to talk a little bit about these units that people are starting to use, and you're probably seeing these in the slides. So ppm basically means parts per million. All right, now what does that mean to you? Well, nothing yet, so just bear with me for a minute. So ppm also is parts per million, but ppm is also known as milligrams per liter of solution. So what that means is that if I take a volumetric flask in a laboratory, and this volumetric flask maybe is a 1 liter volumetric flask, that's 1,000 milliliters, folks. All right, so if you're thinking about volume, think about the grocery store, go back and think about the 2-liter bottle, and that 2-liter bottle, cut it in half, that is a liter. So that amount of solution, that liter, well, I'm putting maybe a few little dabs, a dab-a-doo-ya, into that liter of solution. And these could be measured in milligrams. Well, if I know how many milligrams, maybe just a few specks, that's all that I need, into a liter of solution or solvent, then this is milligram per liter. And that milligram per liter is a concentration that we do like to report sometimes. It's very common. Molarity is great and all, don't get me wrong, but molarity is a joke very often in a laboratory. They push it on you in chemistry 251, 152, 151, but folks, take it from me, molarity is great, but it's not the common unit that we use. So milligrams per liter is also known as ppm, which is parts per million. But Tracy, what does parts per million even mean? Okay, well, here's some analogies to some parts per million, some maybe relationships that you can put into your head. Well, if you had $1 million bills in front of you, 1 million of them, folks. Now just imagine, if you can imagine, $1 million bills. That means a 1 part per million solution. 1 of those dollar bills would be counterfeit. And you would be able to pick out that counterfeit dollar bill, lickety split. It doesn't take long at all with our equipment that we have in a laboratory. So that is a relationship of parts per million that you maybe can conceptualize a little bit into your mind. Well, it's also the equivalent of 1 inch in 16 miles. 16 miles, folks. 16 miles. 1 inch, one little bitty inch in 16 miles of length. That is equivalent to a part per million. 1 second in 11 and a half days. So if we're talking about a 1 part per million, we are talking about a second in almost a 2-week time frame. 1 minute in 2 years. Folks, that's so small. It's so insignificant sometimes when you think about it that way. But we can go this low. We can go this low in a laboratory, and you're getting ready to go that low because you're getting ready to play the water hardness limbo. And 1 car in a bumper-to-bumper traffic jam from Cleveland all the way to San Francisco, almost all the way across the country. 1 car. 1 car in that chain. That is a part per million. So super, super tiny amounts is what we're looking for. Super, super tiny amounts, 0 to 60, 60 to 120, 120 to 180, greater than 180. and now you have a better feeling maybe of what this milligram per liter is all about, otherwise known as part per million. This water hardness will change depending on the country that we live in, or part of the country that we live in. I hope we all live in the United States, but depending on the part of the country that you're going to be in, water hardness does fluctuate a little bit. So as you can tell, we're over here on the East Coast. This East Coast area is all in purple. You can see that all the way through. And that purple area is going to typically be very soft water. So naturally, we don't have to do anything to it. We are the benefits of the East Coast because our water sources are typically very soft. We don't need to purchase water softeners for our homes because they're already soft. And that's just naturally the way it comes for us. But if you were out Midwest, if you were living in the states of Texas or Oklahoma or Kansas or Wyoming, any of these Midwestern states, you're probably looking at hard water, and you would immediately know it if you ever take a trip out Midwest and you stay in hotels or you stay in, Airbnbs or whatever you decided to choose from, because you would tell the difference in the water. And very often people that go out Midwest will go and take showers, they will take baths, they will brush their teeth, they will wash their hands, and they will immediately complain about the way their skin feels. They will say that my skin feels oily. It doesn't feel like I'm clean. It feels like I'm slimy. Well, that's because it's the hard water. That's all that it really is doing. All right. Okay, so let's talk a little bit about lowering water hardness, because I just said that some people can actually purchase water softeners to make their water softer. And this is all basically an ion exchange system. So ion, you now know the definition of that. Exchange means switch. So what we're doing is that we're taking the calcium and we're taking the magnesium in the water, and we are switching that out with another cation that takes its place. So it's like a do-si-do, right? It's almost like a high school prom. You go to the date with somebody, and by the end of the night, that date's probably dancing with someone else. All right, so that is your ion exchange. So ion exchange is going to happen with calcium and magnesium. That's how these systems work, and it's all based on that property and on that system. All right, so calcium is going to be switched with sodium. That is the salt of choice. It's literally salt, and that frees up sodium in the solution. And here we have calcium, maybe in my drinking water sample, and that calcium is contributing to water hardness. I want to remove that calcium so that way my water hardness goes lower. So what I do is that I bring in sodium carbonate, and a little bit do-si-do happens. And a couple walks into a bar, and somebody single comes in, and that couple, part of that couple, the CO3, goes, oh, hubba, hubba. And then they see that calcium, and they leave and drop sodium like a shoe, boo, hoo, hoo. And then the carbonate, CO3, goes and hooks up with the calcium, and bing! Off they go. They leave the bar and you never see them again. And that poor sodium is sitting at the bar having drinks and being very depressed. And you feel kind of sorry for sodium, but that's just the way that it is. Well, magnesium does it too. Magnesium is in a drinking water sample, but instead of sodium carbonate, very often we will add calcium hydroxide to this. What? Wait a minute. Calcium hydroxide? Well, yeah, and this is the reason, because the magnesium will switch with the calcium. So the same kind of story happens here. A couple goes into the bar, hee hee hee, they're all happy and they're all having a good time. And then calcium and hydroxide split because hydroxide sees the magnesium and it goes hubba hubba hey. And then magnesium and the OH come together and whee, off they go. They have a grand old night together. Who knows what they do? We never see them again. And then poor little calcium is left over in the bar and drowning away in these tears. Well, that calcium contributes to water hardness, but that's okay, because this calcium will then go up, and that calcium can react with the sodium carbonate that's already in the system, and now calcium gets revenge, because it just broke up with the hydroxide. and somebody else came in and took the hydroxide away from him. And now calcium's single and he's on the prowl. And now that calcium's going to go and it's going to go, oh, look, there's a couple. And I think that carbonate has their eyes on me. So now I'm going to be the home wrecker. And I'm going to go in and split that sodium and carbonate up. And then I'm going to form calcium carbonate. And that sodium now can have it. So that sodium is kicked out and that goes into your drinking water supply. And we have just removed magnesium and calcium with the use of 2 reagents. Folks, all of this plays off the solubility rules. And for a refresher, here is the solubility rules. So we've talked about this idea that we have brought in sodium carbonate. All right, so if I look at the solubility rules and I need to find carbonate, no. All right, number 6. Number 6 down here, most sulfides, carbonates, and chromates and phosphates are insoluble. All right, insoluble right there. Okay, well, that's not a big deal. That means that this is a solid, but that is going to react with the calcium possibly and give me calcium carbonate. All right, well, if I go back, most sulfides, carbonates, chromates, and phosphates are insoluble. All right, well, that's great. That's great and all. And then I go through and look at calcium hydroxide, making magnesium hydroxide. All right, so calcium hydroxide, most hydroxides are slightly soluble, parentheses, insoluble pretty much, except for barium, strontium, and calcium. So here we introduce calcium hydroxide, which is a solid. Then magnesium takes its place. Now we have magnesium hydroxide that's there. Magnesium hydroxide's not part of the solubility rule. Therefore, it is going to be soluble, folks. So this is the way that ion exchange happens. We're playing off reactivities. We're playing off the way it precipitates out. We're playing off of all of those ionic types of relationships that they have with each other. Here's a diagram of an ion exchanger. So basically what this is a sodium loaded compartment. You can see all of those sodiums that are listed right there. And calcium, whee, it's like a water slide. Whee! And then out the other end. So that calcium flows through and that calcium says, you're going to be picked off, and you're going to be picked off, and you're going to be picked off, and you're going to be picked off. And then all of a sudden, we start to see these calciums get loaded up on the outside of that resin bead, is what we call that. All right, so all of the sodium now just gets flushed out with the drinking water. That's perfectly okay. It traps the calcium behind, and that calcium is eventually going to get full. So what we have to do is that sometimes we have to flush the system, exchange the tanks, we have to replenish the resin bead, or we flood it with a lot of salt. So if you go and have a water softener, and you have this big bag of chunky salt that you are dumping down into a compartment, this is one of the reasons that you're doing that. All right. So now let's talk a little bit about the chemistries of the water hardness titration. So we're going to be using something called EDTA. EDTA stands for ethylene diamine tetraacetic acid. That is what EDTA stands for. I don't know about you, but I do not want to write ethylene diamine tetraacetic acid over and over and over and over and over and over and over. I mean, that's going to make my hand go into a cramp. So we abbreviate it EDTA, of course. So that's what EDTA stands for. EDTA, I want you to think of as having fingers. It's got 4 fingers, actually, and those 4 fingers can wrap around an ion. And when they wrap around an ion, it cages it. All right, so here is a cage, and on the inside of this cage is this poor little metal ion, and it can't get out until something frees it up. Well, this is the whole purpose of using EDTA. And we want to measure how much calcium and how much magnesium there is in my water sample. So what we do is that we add EDTA to that solution, and when we add EDTA, that EDTA will go around and surround the copper and surround the magnesium. And because it surrounds it, it cages it up, and sometimes we call this a chelate. because this is the process of chelation. And sometimes we'll just call this a complex because it is a complex molecule dynamic that we have on our hands. It's not really a bond. It's not really a change in the reagents. We've not really made anything new. They just kind of like to hang out together. They're almost like BFFs. They're BFFs that have caged each other into each other. I mean, it's pretty much what's happened here. Almost like going to your best friend's house and them not wanting you to leave. Ever. You're sitting there watching TV, bored out of your mind for hours and hours and hours. Or you're watching them play video games for hours and hours and hours. All right, these BFFs, those types of BSF, they never want you to leave the house even though that you're not really doing anything. Well, that's kind of the relationship that EDTA and the metal has. The metal cannot get away because the ETA just wants it there because it just likes hanging out with it. And that's pretty much all that it does. So this is the structure of EDTA. And if you take a look, this metal is a positive 2 charge, right? And this COO group, COO group, COO group, COO group, each one of those carries a negative charge. So what will happen is that this molecule will wrap around. But here's the problem. This COO group is not really a COO group as far as the structure of EDTA is concerned. So until we get rid of these hydrogens here, we will not be able to do anything with EDTA. That's the number one concern that we have. But if we could make the EDTA lose the hydrogens, then we can create these negative charges on the EDTA. And when those negative charges are created, those negative charges now hone in on the calcium and the magnesium, especially because they're positive 2s. And they will gravitate toward them, they will capture them, they will cage them, they will chelate them, and they will form a complex. But we have to get rid of the hydrogens. So one of the ways that we get rid of the hydrogens, folks, is that we make sure that we put this in a basic solution before we titrate it. What that means is that we have to ensure that EDTA goes into a basic solution. Now, think of pH. That's why we did this, right? That's why we did the whole lecture, the whole lab on pH. pHs greater than 7 are going to be bases. So what that means is that I've got my sample that's down in here in the bottom of the flask. That sample, we are going to have to add what we call a buffer. And the buffer is going to be a pH of 10 buffer. And the purpose of the buffer is to make sure that I have a basic environment. Because if I don't have a basic environment, the EDTA hydrogens do not get spit off. And those hydrogens, if they don't get spit off, they cannot complex with the calcium and magnesium. So the buffer is very important in this step, and that's why we use it. So we can't just ignore it. You can't just say, oh, well, it's just a buffer. We use a buffer for a reason. Right? It's like everything else. We use it for a reason. We're not going to tell you to add something if it doesn't matter, because it's waste. It's a waste of money. It's a waste of time. It's a waste of energy to make it. So we have to add the buffer, and that is the reason that we add the buffer to this solution before we titrate it. We have to ensure that it's around a pH of 10 before we begin the titration. Now, as you can imagine, titrations really do play off of indicators. And the indicator here that we're going to be using has an abbreviation of EBT. Well, EBT is known by many different things. Used to be known as the food stamp card, pretty much, really. And it's also known as Erie Chrome Black Tea in the laboratory world. All right, so Erie Chrome Black Tea. Erie Chrome Black Tea is an indicator, and EBT could come to the form of a liquid or a solid. And folks, what we're going to be using in this titration, because it's a little bit different than the traditional titrations that you've done so far, we're going to get you to use just the solid indicator, just some powder. We give you some powder, we have you to measure some of it out, knock it down into solution, and folks, you got it. There's your indicator. And what this indicator is going to do is it will turn color, like most indicators do. So Erie Chrome Black Tea, goodness gracious, looks like this down here at the very bottom. I do not, of course, want you to memorize that structure. That is silly. You don't need to know anything about that structure. But what you do need to know is that that structure will change colors depending on what goes on. Well, it's going to gravitate toward the metals. That's one of the reasons that we use EBT. And what you will see is that initially it will be this reddish pink color. And that reddish pink color means there's calcium and magnesium around. That's good because that's what we're trying to measure. So we are going to add EDTA, drip, 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 down into the solution through the process of titration. And that drip, 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 drip of EDTA is going to chelate the metals. And through that process of chelation and making these complex ions or compounds, it's going to slowly remove the calcium and magnesium out of the solution. Little bit by little bit by little bit by little bit. And then when the last remnant of calcium and magnesium are gone, when no more calcium and magnesium are present, the EBT goes crazy. And the EBT goes through withdrawal because that's kind of what it's been eating on. And now there's no more calcium and there's no more magnesium. Oh no, what's it going to do? Well, it ding turns color. It goes from a red pink to a bluish color in the test tube. And that is how I know when the titration stops. So if you take a look up here at the top, this is the Erie Chrome Black Tea at pH of 10. And what begins to happen is that this Erie Chrome Black Tea looks at this OH group and this OH group, and those two OH groups share an M together. It's like a three-way that's happening here. And that M is going to stand for a metal. That metal is your calcium or your magnesium. So if that happens, then this becomes a pink color. And over time, EDTA is getting added into the solution. So Erie Chrome Black Tea has gathered some of the magnesium and some of the calcium that's out there, and it's made it pink. And then as EDTA is coming in, it's slowly chipping away little bit by little bit off the calcium and the magnesium. And sooner or later, the only metal that's left is in the indicator. Well, that calcium and the magnesium is going to be ripped off of there by the EDTA molecule. And when those metals get ripped from the compound, folks, we go back to this, and this solution is blue. So there is my color change of pink when it has a metal that it combined with, to blue when there's no metal present to be found. So those are the colors that we want to look for in this titration. The other thing I want to mention, folks, is that this is not a traditional acid-base titration that we have seen in some of our other titration lab experiments. There's nothing acid and base about any of this, which is another reason that we pull in this titration. Look, my eyes must be crooked tonight. Look at this. All right. So here is the sample, and the sample has a buffer. That buffer is at a 10, but this is not an acid-base reaction. That's not really the purpose of that buffer. The purpose of that buffer is just to make a basic condition, so that way I am priming the EDTA to basically be negatively charged. It's going to remove those protons off the outside. So that sample that has my buffer in it is basic, but it is not an acid and base reaction. The EDTA, ethylene diamine tetraacetic acid. Well, that's an acid that buffers a base. That's not what this is. It's not what this is. Because this is an acid, but this has already lost protons. It's already negative. By the time it gets into this beaker, it's already negative, folks. So we are not relying off of reaction between an acid and a base. That is the misconception with water hardness titration. So EDTA is going to go into the burette. EDTA is going to drip, 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 drip down into the beaker. This beaker is going to have my sample that does have a buffer of pH of 10, but this has nothing to do with an acid and base reaction. This has everything to do with a complex. A complex. That complex is taking EDTA and it's grabbing the calcium through an ion. That's what's happening here. This is negatively charged, this is positively charged, and they come together to make a nice little quaint marriage. Nothing to do with acid-base reactions. It is a complex that's beginning to happen here. Buffers. Tons of different buffers. You've used buffers before. Buffers were used to calibrate pH probes and stuff in the past. So buffers are typically added to some reactions at times just to make sure that we stay at the pH level that we need to be in. These buffers are basically a mix of what we call a weak acid and a weak base. So we have both in there, and we can control the amounts of either, and that will control the pH of that particular buffer. So if I want this pH more acidic, then I'll use more weak acid. If I want this to be more basic, then I use more weak base in order to make that happen. All right. The buffer that you're going to be using in this experiment is a pH of 10-ish that has been made with ammonia. And do not go and sniff this bottle. If you sniff this bottle, you're probably going to pass out because you're going to gag. It will stink and it will burn, and it will probably burn your eyeballs if you take in enough of it. So pretty strong ammonia kind of scented solution. So just don't go putting your nose where it don't belong, and just don't be sniffing bottles in a lab. I mean, that's all that I can say to you. It's basic lab safety. That's what this is. But that buffer, again, very, very important. So here's the rundown of the lab experiment before I show it to you. We're going to place the sample in an Erlenmeyer, and then we're going to make sure that we adjust the pH to 10 with ammonia or hydrochloric acid. Sometimes the sample might be a little high, or we might overshoot it with the buffer and we got to bring that pH back down, and we do that with the addition of hydrochloric acid. We're going to add a couple of specks of indicator powder. That's another reason that we like the titration, because it's not a liquid indicator, it's a solid indicator. It is not an acid-base reaction. It is a complexometric reaction. And then we're going to add EDTA until it turns blue. And we got to go pretty quick about this. We don't want to just wait forever. When we add that, when we get it ready, we want to titrate it as soon as possible. So prep these samples as you go. Do not prep all of them that you need to titrate and then titrate them all at once. You really do want to titrate them as soon as you can, lickety-split. Now, let's talk about the calculations and the stoichiometry just for a little bit. The lab's going to walk you through some of this, but the relationship between EDTA and with calcium, folks, it's a 1-to-1. So that means for every 1 molecule of EDTA, you will bind 1 molecule of calcium, which makes the math a little bit easier as far as we're concerned. And again, we'll walk through the math probably a little bit more in class before you actually do the lab experiment. Once I get the moles of calcium, I then can transfer that to grams of calcium using the formula weight. I can then transfer it to milligrams of calcium. Then if I have milligrams of calcium and I know the liter of sample that I started with, probably like 50 mils, convert it to a liter or something, then I can calculate part per million because I now have milligram and liter. All right, so let's take a look at the lab procedure. A little bit about the lab procedure that you'll be following. This is an ASTM method. It is the actual method that real labs use in the environmental world. And this ASTM is going to be basically the layout of everything that you need. So we did not write this lab. Laboratories do not write this lab. This lab is pulled from a regulatory body. And this person says, listen, this organization, listen, if you're going to do water hardness, these are the steps that you're going to have to follow. So what I would like for you to do before you come to lab is read and review this lab procedure. Make sure that you know what you're doing before you come into lab, because it is very wordy, as you can tell. However, the procedure starts at number 9. You can see that there, number 9 procedure, and it tells you where to start at that point. So if you don't read anything at all, folks, at least go to step number 9 and read the directions that it tells you to do. So we'll touch base on this too in the laboratory, maybe before lab starts. But folks, this is the rundown of the water hardness lab experiment that you're going to be doing with us in this section of the course. All right, so directions of all the reagents are included in the method, the procedures included in the method, and as you notice here on the back end of the method, you will see calculations after calculations after calculations. All right, okay, so there's your target. That's what our plan's going to be. I'll see you in the lab when you get there, and until then, good luck on the pre-lab assignments. Make sure you review the procedure. Again, very wordy. Just know what you're doing, and then we'll talk about it before we get started on that day.